Hello, dear students. We are continuing our lessons, laboratory work by Technological Foundation of Mechanical Engineering. And today is laboratory work number 5, design of technological operation, tuning processing. Write down to your notes the theme of our laboratory work, the purpose and equipment, instrument, and accessories of our laboratory work. So, the purpose of the work is to study the kinematics of the tuning process, equipment and cutting tools, learn how to develop processing technology on a screw cutting lathe, and fill in the necessary technological documentation. And equipment, instruments, and accessories. Screw cutting lathe machine 1K625. Cutting tool through cutting cutter T15K6. Base of the workpiece in the centers. The torque is transmitted by the leash. Measuring tool micrometers from 25 to 50, from 50 to 75, from 75 to 100. Caliper and metal ruler. Write down to your notes the purpose of the work and equipment, instruments, and accessories. Short theoretical provisions. Tuning is the most common cutting method and is used in the manufacture of parts such as bodies of revolution, shafts, discs, flanges, rings, bushings, etc. The main types of tuning works: processing, of external and internal surfaces, processing of ends and ledges, tuning of grooves, workpiece cut, drilling, sinking, and reaming holes, cutting of external and internal threads, processing of shaped surfaces. The cutting process unless is carried out with a rotation main movement transmitted to the workpiece and with a rectilinear translational feed movement transmitted to the cutter. When working on less, different cutting tools are used. Cutters, drills, countersinks, reamers, taps, dies, shaped tools, etc. You can see in this figure the main surfaces of the workpiece and the main movements performed during the cutting process. Once the surface being processed, two, cutting surface, 3, treated surface, 4, the axis of rotation of the workpiece, 5, longitudinal taper feed, 6, transverse feed, 7, cutter, 8, its workpiece, 9, the main rotational movement, 10, small t is the depth of cut. The tuning cutters are the most common tool. They are used for processing planes, cylindrical and shaped surfaces, threading, etc. Structurally, the cutter consists of a head and a rod. At the intersection of the front surface with the main and auxiliary rear surfaces, respectively, the main and auxiliary cutting edges are formed converging at the top of the cutter. Tuning is carried out on machines of the tuning group, which includes screw cutting lasses, turret lasses, vertical lasses, automatic lasses, and semi-automatic machines. The design of the technological process of processing on a screw cutting lathe includes the following main stage. First, selection of technological installation basis and drawings up a plan for the machining of individual surfaces. 2. Development of a technological road for processing a part. 3. Choice of cutting and measuring tools. 4. Calculation of cutting modes and main technological time. 5. Registration of technological documentation. And now let's see some video about tuning on the lathe machines. Tuning on the lathe machines. And we start the first video.
Mechanism of metal cutting. In this video,
Mechanism of metal cutting.
we are going to discuss about the mechanism of metal cutting. Consider a workpiece and tool. During machining, cutting tool exerts a compressive force on the workpiece. Tool, workpiece, chip, tool face, shiny surface, rough surface, flat, relief or clearance angle, shear angle, rake angle. Sheared material flows along the cutting tool face are called chips. Orthogonal cutting process. In this video, we are going to see about orthogonal cutting process. Consider a single point cutting tool, cutting edge and workpiece. Cutting edge of the tool is perpendicular to the cutting velocity. Chip. Here, only two components of forces are active, cutting force and thrust force. Cutting forces in orthogonal cutting. In this video, we are going to see about cutting forces in orthogonal cutting. Consider a workpiece held in the lathe. Tool, chip. Three components of force are acting mutually at right angles. Resultant force R is equal to square root of fx squared plus fy squared plus fz squared. Orthogonal cutting. Three components are reduced to two components of force. R is equal to square root of fz squared plus fxy squared. Oblique cutting process. In this video, we are going to see about oblique cutting process. Consider a tool, cutting tool edge and workpiece. The cutting edge of the tool remains inclined at an acute angle to the direction of tool feed or work feed. The direction of chip flow velocity is at an angle with a normal to the cutting edge of the tool. Here, three components of force are active: cutting force, radial force, and thrust force.
And now we start the next video, lathe operations.
Facing operation. In this video,
First type of operation, it's facing operation.
Operation in the lathe. Facing is an operation which produces flat surfaces.
Facing.
Facing tool.
We use the facing tool.
In this operation, the tool is bent at right angles to the axis of the workpiece. It reduces the length of the workpiece. Various types of lathe operation will be discussed in the next videos. Turning operation. In this video,
Next type of operation is turning operation. Cylindrical turning.
Machining operation in which excess material is removed by rotating the workpiece against a cutting tool. Workpiece, feed, that is F, depth of cut.
Knurling operation. In this
Knurling
video,
operation.
we discuss about knurling operation in the lathe. It is the process of indentation of various forms on cylindrical surfaces. Knurling tool. Workpiece. A knurl tool is held in tool post and pressed against the rotating work. It is done to provide grip on boulders and screw heads. Grooving. In this video, we are going to see about grooving operation.
Next time, the operation is
also
grooving.
known as
Grooving operation.
undercutting or necking. Consider a workpiece held in lathe. The grooving tool is fed crosswise.
We
against
use
the
grooving
rotating
tool
workpiece.
during grooving operation.
A groove is the location of an indentation in the part. This indentation can be square, round, or angular in the shape. The function of a groove is usually to allow room for a fitting part, such as a rubber O-ring. It could also be the place where another part fits into this part. Grooves also provide a relief in the backside of a thread where the thread terminates. Drilling. In this video, we will discuss the drilling.
We can
operation
do
of
the
lathe.
drilling operation on the lathe
It is
machine.
the process of making holes on workpiece. The drill is fed slowly into the workpiece, which is revolving in a chuck.
Workpiece is revolving in the chuck.
Drill tool. The drill is held stationary in the tailstock spindle. Reaming. In this video, we are going to see about reaming. Reaming is the operation of finishing and sizing a hole which has been previously drilled or torn. Consider a workpiece held in lathe. The tool used is called reamer, which has multiple cutting edges. The reamer is held on the tailstock spindle, either direct or through a drill chuck, and is held stationary while the workers revolve at a very slow speed. The speed varies from 0.5 to 2 mm per revolution. Hence, reaming is done. Boring operation. In this
Next
video,
time of
we will
operation
discuss the
is
boring
pouring
operation.
operation.
Boring is the operation of enlarging the previously drilled hole with the aid of single point cutting tool called boring tool. Workpiece, boring tool. If the hole is enlarged only through a certain length, then it is referred as counter boring. If the tool is feed at an angle to the axis of rotation, it is called internal taper turning. Enlarged hole, parting off. In this video, we will discuss the parting off operation on the lathe. Workpiece, cutting off tool, parting off is the operation of separating the finished workpiece from a bar stop. The operation involves feeding the cutting tool into the rotating workpiece.
And now you should look at the video with different types of lathe machine.
In this video, we will discuss about engine lathe and its components. Now, see the 3D model of engine lathe and its components.
Components of
It
lathe
is the
machine.
most common type of lathe and is widely used. The
It's widely
workpiece is
used
clamped by
lathe
the
machine.
centers in the lathe. Main parts of engine lathe are headstock, tailstock, live center, dead center, carriage. In earlier days, it was driven by steam engine and hence it was called engine lathe. Bench lathe. In this video, we will discuss about bench lathe and its components. Now, see the 3D model of bench lathe. It is a small lathe that can be mounted on a workbench. Main components of bench lathes are headstock, tailstock. It has all of center lathe, the only difference being the smallest size and mounting. It is used for machining small parts accurately and economically. Tool room lathe. In this video, we will discuss about tool room lathe. It is meant for application of tool making which require accurate and precision machining. It has more range of speed and feed also greater rigidity for turning accuracy. Turret lathe. In this video, we will discuss about turret lathe and its components. Now see the 3D model of turret lathe. Main components of turret lathe is headstock, hexagonal turret head, carriage, lathe bed. These lathes are semi-automatic. The tailstock is replaced by a hexagonal turret. These lathes have provision to hold a number of tools and can be used for a wide range of operation. Automatic lathe. In this video, we will discuss about the automatic lathe and its components. See the 3D model of automatic lathe. Let us see the main components of automatic lathe is chuck, tailstock, workpiece, turret head, carriage. Reciprocation feed. The tools are automatically fed to the work and withdrawn after work is completed. Turning tool. Cross feed, that is depth of cut. Tool change. They require little attention of the operator since entire operation is automatic. CNC lathe. In this video, we will discuss the CNC lathe. It is the automatic lathe which is programmed in part programming code. Controlling the NC machines using computers. Radical changes in industries due to this machinery. Features are variable speed edge stop, automatic tool changers, anti-friction lead screws.
Constructional features of a lathe. In this video, we will discuss tailstock assembly, dead center, carriage assembly, compound rest, apron, cross line, tool post, lathe bed, guide base, lead screw, feed rod. Specification of lathe. In this video, we will discuss about the specification of lathe. Specification of lathe described in the following ways: headstock, tailstock, lathe bed, swing of workpiece over lathe bed, the height of the centers measured over the lathe bed. Swing over the carriage, swing or diameter over carriage. Distance between centers, maximum job length in millimeter that may be held between the centers. Overall length of bed, bed length in meters, which includes headstock length. Lathe bed. In this video, we will discuss about the lathe bed and its components. Main components of the lathe bed are bed base. Bed is the base or foundation of the lathe. It supports other parts of the lathe. Inverted V bedway, flat bedway, inverted V bedways, and flat bedways provide support for carriage and tailstock movement. Headstock. In this video, we will discuss about the headstock. It is the important components of lathe. Now see the parts. Headstock, workpiece, chuck. Headstock provides a mechanical means of rotating workpiece. Hollow spindle. Headstock consists essentially of a hollow spindle. Power source, that is motor. Power transmission, that is belt drive. It also consists mechanism for driving and altering the spindle speed. Back-geared headstock. In this video, we will discuss about the back-geared headstock mechanism. There are two types of mechanism used, named as back-geared headstock mechanism and all-geared mechanism. The back gear arrangement is used for reducing the spindle speed, which is necessary for thread cutting and knurling. Back gears P1, P2, L, fully pinion, P1, full gear, G1, spindle, lever, lock pin, Pole pulley. There is a step pole pulley on the lathe spindle which can freely rotate. A pinion gear rotates along with the pulley. Back gears not engaged. Power transmitted from P1 to G1 and spindle. The spindle rotates at normal speed. Spindle. Back gears engaged. Lock pin released. Power is transmitted from P1 to P1 to P2 to G1 and spindle. The spindle rotates at reduced speed. Tail stop. In this video, we will discuss about the tail stop. It is the important components in the lathe. Tail stop. Tail stop is a non-rotating part of the lathe. It supports right end of the workpiece. Tail stop spindle, dead center. Dead center supports the workpiece. Spindle clamping lever, hand wheel, screw, bedways, clamping board. Tail stop can be moved left or right over the bedway. When supporting heavy jobs, life center is used which rotates along with the job. Carriage. In this video, we will discuss about the carriage. Carriage components are saddle, cross slide, compound rest, tool post, apron. Saddle, head-shaped casting slides along the bed base. Cross slide gives cross-beam motion to the cutting tool. Compound rest supports the cutting tool. Tool post clamps the tool. Apron attached to the saddle. It has gears, control levers, and clutches for moving carriage and cross slide. Working principle of lathe. In this video, we will discuss the working principle of lathe with the help of basic lathe operation. Now, we see 3D model of lathe. Let us see the principal components of the lathe. Workpiece, chuck, tool post, cutting tool. In a lathe, the workpiece is held in a chuck or between centers and rotated about its axis at a uniform speed. The cutting tool held in tool post is fed into the workpiece to the required depth and in the desired direction. The workpiece is rotated and the cutting tool is moved relative to the workpiece. That is why the lathe is also called as turning machines.
And the last one video about cutting tool geometry. Cutting tool geometry.
Cutting tool geometry. In this video, we will discuss about the cutting tool geometry. Most important angles in tool geometry are rake angles and clearance angle. Some of the important tool geometry are side rack angle, shank, face, back rack angle, end cutting edge angle, nose radius, end relief angle, side cutting edge angle, side relief angle. We will discuss the form tool method taper turning in the lathe. Headstock, tailstock, carriage. Form tool method is one of the simplest methods used to produce short taper. Workpiece, a broad nose tool having a straight cutting edge is set onto the work at a half taper angle and is fed straight into the work. Taper turning form tool. Taper turning operation. Taper length should be less than tool cutting edge length. Tailstock set over method. In this video, we will discuss the tailstock set over method taper turning in the lathe. Workpiece, chuck. Tailstock set over the axis of rotation, taper turning tool, tailstock, taper turning operation. Axis of rotation of the workpiece are shifted at half an angle of taper to the lathe axis. Tailstock set over compound rest method. In this video, we will discuss the compound rest method taper turning in the lathe. It produces short and steep taper. Workpiece, tool, chuck, headstock, compound slide. Compound rest is swiveled to the required angle and clamped in position. Taper turning attachment method. In this video, we will discuss the taper turning attachment method taper turning in the lathe. Taper turning attachment. Bracket, guide bar, workpiece. Guide bar can swing at any required angle of the taper. Taper turning attachment. Guide bar, the tool moves parallel to the guide bar to produce taper.
And now we continue our slides. So, as technological mountain bases, that is surfaces with which the part is oriented on the machine relative to the cutting tool, different workpieces, as well as center holes and end planes can be selected. The method of installing and fixing workpieces on a screw cutting lathe is chosen depending on the size, rigidity, and accuracy of the manufactured part. If the workpiece is installed in the machine chuck, then the length of the clamped part must be at least 1/3 of the total length of the workpiece, and the length of the protruding parts should not exceed 2-3 diameters. Longer blanks or workpieces are fixed in the chuck and pressed with the rear center into centered end of the blank or workpiece. In the case when the surfaces of the part do not allow it to be installed in the chuck, a typical technological bases are created, center holes, and the part is installed in the centers. She receives rotation with the help of less cartridge. The plan of route for processing individual surfaces is selected depending on the specific accuracy and surface roughness according to table 2.1 in the appendix. When choosing a processing route, the details are guided by the following recommendations. First of all, technological bases are processed, then other surfaces. Moreover, processing should be carried out in parallel. The part processing route must be with finishing transition at the end of the route. The treatment of easily damaged surfaces, external threads, etc. is also often carried out. When designing a tuning operation, one should strive for a minimum number of part installation. The choice of cutting tool is influenced by the processing method, configuration, accuracy, and quality of the surfaces to be machined, and the material of the workpiece. Straight and bent through cutters are widely used, which allow not only longitudinal but also transverse shaping. Thrust-through cutters are suitable for machining workpieces with small shoulders. The scoring cutter allows you to process various and other surfaces with longitudinal and transverse feed. The cutting tool is made wholly or partly from tools, steels, and hard alloys. High-speed, hard alloy steels are widely used for the manufacture of various tools, most often drills, countersink tabs from tool materials. Hard alloys are divided into metal ceramic and mineral ceramic and are produced in the form of plates of various shapes. Tools equipped with tungsten garbage inserts allows higher cutting speed than HSS tools. The most widely used ceramic metal hard alloys. It's WK4, WK6, 6 VK8, etc. For processing cast iron, not ferrous metals and non-metallic materials, plastics, glasses, etc. Tungsten, titanium, T5K10, T15K6, T14K8, etc. for processing all types of steels. The most common tool for measuring the dimensions of part obtained after raw and semi-finished processing is a caliper of the T1 type with a measurement accuracy of 0.1 millimeters. A micrometer with a measurement accuracy of 0.005 millimeters is used to control the diameter during precise and fine sharpening. Productivity and quality of mechanical processing are largely determined by cutting modes, the elements of which are cutting depths, T in millimeters, feet, S suffix 0 in millimeters per revolution, cutting speed, V in meters per minutes. The depth of cut is determined mainly by the machining allowance, which is most productively removed in one pass. However, it is often necessary to remove the total allowance in several passes. 60% for roughing, 35 millimeters, 20 or 30% for semi-finishing, 2-3 millimeters, and 10 to 20% for finishing, 0.51 millimeters. With the roughness parameter of the threaded surface, RA is equal 3.3 micrometers, and depth of cut T is equal 0.5 from 0.5 to 2.0 millimeters. If roughness, parameter of roughness RA is more than 0.8 micrometers, then depth of cut T will be equal from 0.1 to 0.4 millimeters. Feed for external rough shaping is taken according to table 2.2 from appendix, and for fine shaping according to table 3. The selected feed rates are compared with the passport data of the machine, and the smallest values that are closer to the calculated ones are accepted. The cutting speed for external, longitudinal, and transverse shaping and boring is calculated by the empirical formula 2.1. Please write down this formula to your notes, where in this formula T is stability, that is the period of operation of the tool before blunting in minutes, the average value of stability with one instrument processing up to 60 minutes. C suffix V. C suffix V, a coefficient that takes into account the type of processing, the material of the part, and the cutting tool. K suffix V, correction factor. And MXY. MXY are exponents. KV will be equal K suffix MV multiplied by K suffix NV multiplied by K suffix UV. In the formula, KMV is a coefficient that takes into account the quality of the processed material. K suffix NV is a coefficient reflecting the state of the workpiece surface. For workpiece rolled, K suffix NV will be equal 0.9, forging and stamping 0.8. K suffix UV is a coefficient that takes into account the quality of the tool material. The spindle speed is calculated using the formula 2.5. In this formula, small d is the diameter of the threaded surface. V is cutting speed. The obtained rotation frequency should be compared with the passport data of machine and accept the nearest smallest value. Then the actual cutting speed is calculated using formula 2.6. Actual cutting speed and the last formula, the main technological time in minutes, is found by the formula 2.7. T suffix 0 is the main technological time. Small l is the length of the threaded surface. E, the size of the indentation of the cutter. It will be equal from 1 to 2 millimeters. I, the number of paces. S, it's feet. S suffix M, it's minute feet. Minute feet. The sequence of practical work, of laboratory work. Familiarize yourself with methodological guidelines and recommended literature. According to the initial data issued by the teacher, draw the details, like in figure 2.2. The output data contains the material of parts, the parameters of the processed surface, the accuracy, and the roughness of the processed surfaces. These parameters you can find on the last slide of this presentation. Please, last slide. Last slide, it's table A suffix 8.1 initial data. Use your variant and you can find dimensions of the part D suffix 1, D suffix 2, L suffix 1, L suffix 2. Surface precision quality of surface 1 and surface 2, roughness, RA in micrometers, A and B, and material. For example, cast iron or steel. Then develop a technological process for processing the part. Complete a report on the progress of the work. You should calculate all the parameters using the formula from 2.1 to 2.7 for each operation. Content of the report, detailed drawing, output data or initial data, justification of the choice of technological process, calculation of cutting modes, debugging, sketch. You can use the appendix with the tables, and you can choose the parameters from these tables. Table 1, empirical accuracy and roughness when machining on the lathe. Table 2, fits during rough tuning with cutters with hard alloy and high-speed steel plates. Table 3, fit during finishing tuning. Table 4, the value of the K suffix G coefficient and the degree indicator N suffix V. Table 5, correction coefficient K suffix UV which takes into account the influence of the tool material on the cutting speed. Table 6, value of the coefficient C suffix V and degree indicators X, Y, M during external tuning. And initial data, it's your variant for calculating. So you can see content of the report. And now you should start your calculation. When you finished, load your answers to our course and send me to Telegram group. If you have questions, you can write to our Telegram group. So start your work. Our time is finished for today. Our laboratory work is finished. Goodbye. Have a nice day. Thank you for your attention and see you next week. Goodbye.